I'm very happy to talk about the paper towards revealing the mystery behind chain of thought, a theoretical perspective. And our talk will be divided into several parts. First, I will give a brief introduction on the chain of thought and large language models, and then I will formulate the problem in a theoretical perspective by giving some preliminary, such as notations and settings. And then I will answer the question of why chain of thought is powerful via two aspects. First, I will talk about some specific problems, such as the important mathematical problems. I will show that chain of thought is the key to solving some representative mathematical problems, such as arithmetic or equations. And then I will generalize the analysis by focusing on general problems and show that chain of thought can solve a general class of problems known as dynamic programming. And next, I will give some discussions on the architectural relationship for the theoretical results. For example, how our results can translate to some efficient versions of transformers. And finally, I will present some experimental results. Okay, so I will first give a brief introduction. It is well known that large language models have demonstrated emergent capabilities in various aspects, such as generation, question answering, mathematics, coding, reasoning and planning, and decision making, and etc. And most large language models follow the autoregressive design paradigm. The main idea is that various tasks can be uniformly treated as sequence generation problems. For example, consider the following translation task. We can just we can just use a prompt, translate English to French, and possibly with some in-context examples, and finally with our input example. And then the large language models will generate the subsequent tokens based on our question prompt. And all of this generation process is in an autoregressive way. Chain of thought is a very crucial technique for dealing with tasks that involving mathematics or reasoning. For example, here is a illustrative example on chain of thought. For some basic tasks involving some arithmetic calculations, if we directly input with the if we directly let the large language model to generate the answer, the output is usually wrong. This happens even if we give some in-context learning examples, such as the few shot setting. But if we add some prompt to let the large language models generate a reasoning chain, such as let's think step by step, or with some few short chain of thought examples, then large language models can output a complete reasoning chain and finally output the correct answer. So this is a very intriguing experimental phenomenon. How can we understand it in a theoretical perspective? Actually, there are many questions regarding theoretically understanding power of chain of thought, such as the first question is relevant to this talk, but also we can study other theoretical questions, such as how prompt can trigger can trigger COT generation, or how COT can emerge from large language models trained over massive data. But here we will mostly focus on the first question. To answer this question, we will further divide the question into two parts. First, the question is, are there indeed inherent limitations of large language models in directly solving these tasks without chain of thought? So this will point out the limitations of standard generations. And the next question is, what is the essential reason behind the success of chain of thought? This will answer the positive results of chain of thought generation. Okay, so next I will talk about the setup of the theoretical results. First, let me formulate the autoregressive transformers. Here, the input is just a sequence of length n. And for each token Si, we first translate the Si into an embedding Vi plus Pi. Here, Vi just depends on the token Si, and Pi is the positional embedding. And then we can group all the embeddings into a matrix called X0. And then there are L transformer blocks, each of which transforms the input via the following equation. Here, the attention, the most important part is the attention, multi-head self-attention layer. And following the self-attention layer is also a feed-forward neural network with a non-linear activation, such as G-loop. And after the several blocks, the final output, XL, is then used to predict the next token as n+1 via a softmax classifier. And the next token is then concatenated to the end of the input sequence S. And then the above process can be repeated multiple times until generating an end of sequence token. Okay, so next I will answer the question of why chain of thought is powerful. To answer this question, we can first choose some simple settings. For example, the mathematical problems. This setting is very important because it is known that transformer-based large language models have exhibited surprising mathematical abilities in various aspects. So if we can answer why chain of thought is powerful in mathematical settings, it may pave the way to answer the problem via general settings. To answer this task, we can choose some representative and very simple tasks, such as the arithmetic and equation. Here we will focus on two setups. One setup is to directly generate the answer, and the other setup is to generate a complete chain of thought solution. Okay, so let me first give some illustrations how the representative large language models deal with mathematical tasks via two different ways. Here, I use a prompt to tell the GPT. Direct means directly generating the answer, and chain means generating the intermediate steps. And if we let the GPT to directly generate the answer is actually wrong. We can check it. And also, if we let the GPT to generate a chain of thought solution, although the output is very long, the final answer is actually correct. And also, we can use it to solve the equation problem. Here, given a linear equation, if the GPT directly generates the answer is also wrong. And if we let it to generate a chain of thought solution, it outputs a very, very long chain of thought, but the answer is correct. Okay, this is an illustration, but now we need to rigorously define the problem formulation so that we can study it in a theoretical perspective. First, one challenge is that for these mathematical problems, the input is usually floating point numbers, and the output is also sometimes floating point. So this makes our analysis complicated because we cannot store these floating point numbers in a precise manner by using a computer model. So to simplify the setting, we consider the discrete versions of arithmetic and equation. Specifically, we consider the finite field so that all numbers and integers ranging from 0 to p-1. Here, p is a prime number. This setting is actually similar to the real-valued setting because all the properties of arithmetic is similar. For example, uh, if we want to solve equation in a finite field, the process is basically the same. We need to use Gaussian elimination to eliminate variables step by step and finally generate the answer. So the process is actually the same, but this makes our analysis simpler. Okay, so here we can define a chain of thought. For the arithmetic expression, for each step, we just calculate one operand and just copy other numbers and operands. And for the linear equation, for each step, we can just eliminate one variable. So we use the Gaussian elimination to generate a chain of thought solution. Okay, and before presenting our theoretical result, we also need a concept called the log precision transformer. This is actually a practical setting. Intuitively, it refers to a transformer whose internal neurons can only store floating point numbers within a finite precision. And the precision is O log n bit. Here, n is the maximal length of the input sequence. So this means that we cannot exactly store the floating point number. We can only have finite precisions. So why using log precision? The log means that the number of values its neuron can take is polynomial in the input length because the bit is logarithm in the input sequence length. So the number of values is polynomial. This is a very reasonable assumption because, for example, if we want to store some positional embedding, the number of values the neuron can take is at least should be linear in the sequence length. And on the other hand, polynomial is a practical assumption because for the modern precision, for the modern machine precision, it is usually 16 or 32, which is actually which is basically just logarithm in the maximal sequence length, such as thousands or millions. We can just take logarithm, and the answer is similar to 32. Okay, so then I can present the first result. Here it is a negative result showing that directly generating the answer without COT is hard for transformers. This is based on an assumption TC0 is not equal to NC1, and I will explain this assumption in later slides. But the result is actually easy to understand. For any prime number P and integer L, and any polynomial, there exists a problem size N such that no log precision autoregressive transformer with a constant depth L and a hidden dimension D, polynomial in N, can directly solve the problem. And the two items are similar. The first item focuses on arithmetic problem, and second item focuses on equation problem. So this theorem implies that in order to directly output the answers, the size of the model must grow super polynomially in the input length. Because if the model size is fixed, then we can always find a large enough n's so that the model cannot solve the problem size n. And the super polynomially size is due to this result, d less than qn. So as long as the dimension is polynomial in n, this negative result holds. So this is a very maybe strong result because super polynomial is a very hard condition and it's hardly satisfy in practice. So this means that transformer cannot solve these problems at scale. So how can I prove this theorem? This is based on a key insight called circuit complexity. This is why we need this assumption TC0 not equal to NC1. The TC0 and NC1 are two standard computational complexity classes, and it's widely believed that the NC1 class is strictly larger than TC0. So what does this mean? This means two computation model. If we consider a log precision transformer, actually it is also a computation model because we can implement it using a computation, using some basic computation rules. For example, transformers is composed of linear layers, softmax activations, softmax attention, and nonlinear activations. All of these basic computations can be simulated using a computation model if we restrict the precision to be finite. So this computation model will correspond to the TC0. This is already proved in a recent paper. It shows that a pure transformer represents a class of shallow circuits with complexity upper bounded by TC0. But on the other hand, we can show that our problems, such as arithmetic and equation, cannot be, at least should be solved by this harder computation model called NC1. So NC1 actually means using some basic logical gate such as AND, OR, and NOT, but each gate can only accept two inputs, and we can stack these gates in at most logarithm in the input size layer. So the layer is upper bounded by the logarithm of the input size. This is means NC1. And TC0 is a constant depth circuit, but the basic gate can be more powerful, such as we can use in the threshold gate with multiple input. I just basically talk about this. It's not important for understanding this theoretical result. Okay, so the final step is to show that our problems such as arithmetic and equation are lower bounded by the NC1 computation model. This can be proved by using reduction. For example, we can show that computing the arithmetic equation is harder than computing solving a question called the Boolean formula evaluation, because Boolean formula evaluation can all be solved using basic add and multiply these computations. So it's easy to understand that arithmetic is harder than Boolean formula evaluation. And similarly, we can prove that equation is harder than another question called the automaton membership testing. And all of these questions are hard enough, and it's lower bounded by the NC1 class. So as long as TC0 is strictly bounded by NC1, we show that there is a gap. So this hard problem cannot be solved by standard transformers without chain of thought. So why this result hold? Actually, transformer has a very low level of parallel complexity. So if the problem cannot be solved in parallel, it cannot be solved well by transformers. This is the key insight of the proof. Okay, and next I will talk about another direction, the positive result. So how about generating a chain of thought solution? After generating a chain of thought solution, we can prove that a constant size model, such as depth L equals to 5 and 5 heads and a constant hidden size independent of the problem size. With a constant model, the model can generate correct chain-of-thought solution for all input in the problem arithmetic and also equation. And moreover, all parameter values are bounded by poly n or poly m. Here, n and m are the problem size. So for this theorem, the proof is actually done by construction. We can just construct a transformer with certain parameters that can achieve our goal. The proof reveals the significance of several key components in the transformer design. First, we can show that one attention head can perform the following two basic operations. One is the conditional copy, and the other is conditional reduction. Here, conditional copy means to copy previous tokens that satisfies a condition. For example, we want to copy the nearest equal sign. This is a simple task. We copy the nearest sign, equal sign, this symbol, this. For example, we want to find the position of the nearest equal sign. This can be done via one attention head. And this is called the conditional copy. And conditional reduction is similar. We need to calculate the average of the hidden neurons satisfies a condition. This can also be done by using an attention head. Then we can use multiple attention to perform multiple copy and reduction operations in parallel. Next, the MLP can perform some point-wise calculation, such as multiplication, linear transformation, conditional selection, and lookup table. By combining all of these basic components, we can stack multiple layers to achieve a complex goal. Oh, and finally, also note that residual connection can reserve the historical information. So we can stack multiple layers and form a complex computation model to solve the problem. And let me further make some discussions of the theoretical result. First, our qualitative theory is actually practical because due to this final sentence, all parameter values are bounded by poly n. This means that the parameters values are not large and can be implemented using log precision. This matches the practical setting. And also, for these problems, the COT format is very standard. This is similar to how human write solutions. So our theoretical result is kind of practical that reveals the practical settings. And finally, comparing the positive result and negative result, one may ask, how can large language models equipped with COT bypass the impossibility result? So the reason actually lies in the effective depth of the transformer circuit. Without COT, transformer must output the answer immediately using one step. So this computation model has a low level of parallel complexity. But if we enable the large language models to output the COT, then the COT step can depend on the input size. This means that the effective depth of the transformer circuit is no longer constant. And so the expressivity can go far beyond TC0. Because TC0 is a computation model with constant depth. If we allow the transformer to output a very long COT, the depth can go much beyond constant. So the expressivity can be boosted a lot. Okay, so this is the first part of our theoretical result. And next, we can generalize the analysis by focusing on general problems beyond the mathematics. Here we can use a unified framework called the dynamic programming. We can show that as long as a problem can be formulated in a dynamic programming setting, then transformer with COT can always output a correct chain of thought solution. So the basic idea of dynamic programming is very similar to the idea of chain of thought solution, because dynamic programming just breaks down a complex problem into a series of smaller subproblems that can be tackled in a sequential manner. In a dynamic programming, we have some basic concept. First, we need the concept of states, and we need the concept of transition. We decompose a problem into multiple states, and each state can be computed based on some previous states with a transition function. This will form the order of the states. So we can solve the problem based on the order of the states, and then finally obtain the answer of the whole problem. So this decomposition is very similar to the chain of thought solution. We can also see our formulation in a later slide. So to study the dynamic programming in a theoretical way, we need to define some notations. Here, the state is denoted as dpi, where I is the ID. And each state can be computed based on some previous states, h1i to hki. And here S is the input, and F is the transition function. So this dependency will create a DAG that is directed as acyclic graph. So we can follow the DAG to solve the problem. And there are also some examples of the DP. For example, the longest increasing subsequence, added distance. These are very classic DP problems that we can formulate within the framework. And to generate a COT, we can just use this format. After the input sequence, maybe several inputs, we then compute the states one by one, following the DAG order. And then finally, we output the answer. This COT format is very natural in solving dynamic programming problems. And the theorem is also straightforward. We just show that a constant size transformer can solve the dynamic programming problem as long as the problem can be formulated using this format. Also, the parameters values are bounded by poly n. And the proof is also similar. We also use attention head to extract the previous state information and also input sequence information, and use the MLP to perform the pointwise calculations such as the transition function f. And we just use multi-head attention to copy multiple values of previous states. And also the residual connection is used to store the historical information. Yeah, that's basically the same as before. Okay, and for the impossibility result, we can also show find a hard instance. We can find some DP problems that are intrinsically hard to be solved by a bounded depth transformer without COT. One celebrated example is the context-free grammar membership testing. This is known to fall outside the TC0 complexity class, so it cannot be solved by a transformer without COT. But with COT, we can solve this problem. And it is known that the context-free grammar membership testing is a very hard problem. The complexity is p-complete, so this also means that with COT, transformer can solve even p-complete problems. Okay, so we have already talked about the a full picture of the theoretical power of chain of thought for standard transformers. And for the next part, I will briefly discuss how these results can transfer to more general architectures beyond the standard transformers. This is also a recent paper published in SML, so not the original newest paper. But I will briefly talk about the extension of our results. So transformers suffer from quadratic complexity due to self-attention. In light of this, many subsequent works propose some efficient versions of transformers, such as sparse attention, kernelized attention, and recently proposed state space models can also be seen as an efficient version of a transformer because it is closely related to some transformer model. And all of these architectures have subquadratic complexity. So we can ask similar questions. How powerful are these efficient architectures? And can this efficient architectural design really save computation? We can use our previous framework to understand whether these models can solve complex tasks with chain of thought. And if it can solve, what size is needed for these architectures? So recall our basic result. Autoregressive transformer of constant size can solve general DP. And the complexity is just square in the sequence size because the transformer itself is of constant size. So the computation is quadratic in the input size. And for the main result, we can show that for both sparse transformer and kernelized transformers, they can also solve general DP using the same chain of thought solution, but the required size must grow with the problem size. This means that, for example, for sparse transformer, the hidden dimension size must scale like square root L. This is in contrast with the baseline standard transformer. Here, the hidden dimension is constant, does not depend on the problem size. But for sparse transformers, the hidden dimension must grow with the problem size. But since the sparse transformer is efficient, when combining these factors, both the efficient and the growing dimension, the result is that the complexity is still square in the problem size. This is very interesting as it is the same as standard transformers. So this actually says sparse transformers are not more efficient than standard transformers in solving dynamic programming tasks. And also for kernelized transformers, we have the same result. The complexity must grow square in the sequence length. So our framework can be used to study these general architectures, and the result is maybe interesting. This shows that these efficient transformers are not, at least not efficient in solving dynamic programming tasks. Okay, and we also discuss more on this phenomenon. We show that if we restrict the dynamic programming task, we consider just a subset of these dynamic programming problems that satisfies the so-called locality assumption, then these efficient transformers can be more efficient. Here, locality means that for a DP problem, each state only depends on the recent states instead of all the historical states. This is somehow reasonable assumption in some problems, because for some problems, if we compute the intermediate states, each state may only depend on the previous one state or previous two states. If we have this relation, then efficient transformers can still be efficient in these problems. Okay, and the concrete result is here, and we already discussed it, so we can skip. Okay, and finally, let me talk about the experiments. Uh, uh, so we first talk about the standard experiments. Here, uh, we have the arithmetic expression, linear equation, and dynamic programming problems. You can see that when the problem size get larger, standard transformers cannot solve it. The accuracy is always below 50%. But if we use the chain of thought, here the purple bar means the chain of thought case, we can always achieve 100%, approaching 100%, even if the problem size gets larger. Also, we conduct experiment on the length extrapolation and show that if we train the transformer using some smaller size, problem size, it can generalize to some longer problem size if we're using the chain of thought format. Okay, and for the efficient version, we also run some experiments showing that indeed, when the problem size gets larger, the required dimension, hidden dimension also grows for the efficient transformers, but not the standard transformers. Yeah. Okay. So finally, let me give a summary of this work. Uh, oh, so we basically show that chain of thought can solve some uh, simple problems such as arithmetic and equation, but also can solve some general problems known as dynamic programming. And without this chain of thought, we need a prohibitive large size to solve the problems, like grow super polynomial in the input side. But with COT, we can just use a constant size transformer. So this answers the power of COT from an expressivity perspective. And also, we have already talked in the initial slides that there are other directions to understand the power of COT, such as prompt and the model size, and also how do COT emerge when training LLMs with massive data. This will deal with other problems such as generalization and optimization. And finally, we can understand the architectural influence of the COT generation. For example, we show that sparse transformer and kernelized transformer are not efficient in solving COT with dynamic programming. So whether other architecture can help is also an open problem for future work. And that's my talk today, and thank you for listening.